So we are going to finish off this day with a keynote by Stephen Wittens, who's going to be introducing Use.GPU, which looks like a very fascinating take on reactive declarative 3D graphics that allows people to be way more productive than otherwise possible. A fun fact about Stephen Wittens is that most people know him as the guy with that header thing on his website. And if you go to his website, which you definitely should not do right now, because there is a soundtrack, it is acko.net, acco.net. You will be blown away. This is the best header of any website of all time. So please join me in welcoming Stephen Wittens to the stage.
Thank you. Hello, thank you for coming. I know it's been a long day. So this is a talk about graphics. Usually when we talk about graphics, we talk about who has the prettiest pixels, which renderer runs fastest, and how many triangles. And the thing is, that's not what this talk is about. This helmet is rendered with Use.GPU. That's kind of table stakes now. They won't let me into the graphics clubhouse if I don't do this. So, but it's pretty much the shiniest thing in the talk. What is this about? I would say it's about who has the most versatile pixels. There's a lot of different things you can do with graphics, and I think a lot of it has been narrowly focused on certain things. But if this story has a start, it starts with a client. I freelance, I work by myself, and a client might ask for certain things, such as a configurator. I'm not affiliated with this company, but a client did show me this. And so what is this? This is sort of a little, I don't know, bungalow configurator that has lots of options. You can choose all sorts of things, and the 3D model updates as you do so. It's very polished. It's very pretty. This is certainly very impressive. But there's a big problem with this. What's the problem? We call it the permutation problem, which will probably annoy the more mathematically inclined in the room, because it's about every combination being hand-baked and coded. That's why this looks so pretty, is because all the light is painted on. So somebody had to assemble the assets for all the different parts that you can turn on and off, and then write code to do so as you interact with the part on the right. And it's all custom. I don't know how much it cost, but the price tag of the unit might be a hint as to how much the website cost. I don't know. Another thing they'll ask for is data visualization. And there is a lot of software for this out there. Like, this is DecGL. I like DecGL. I've worked with it before. There are others. But they all have the same problem, which is if you want to really customize them, you have to fork them. And the rule is generally don't look inside. And there's many different reasons for it, but if I had to sum it up, I'd say every sufficiently complex renderer contains an ad hoc version of React. I think that's true. What else might be difficult? This is maybe going to surprise you. 2D vector graphics on a GPU, something like this, CAD. It's a lot harder than it seems, even though on a CPU there's thousands of libraries that do this. 3D is a little bit harder. So something like this, rendering surfaces mixed with vector graphics that are properly scalable, that look smooth when you get right in there. It's not obvious at all. So the client asks, we want a 3D house configurator, data visualization, CAD app, preferably with transparency and global illumination. Can you build it? And what do I have to tell them? Yeah, I can, but GPU will take N weeks, months, or maybe even years, and you won't be able to maintain it. And the big question is, why not? This should be profoundly weird that there's this segment of our industry that is so hyper-specialized that it's a non-starter for many companies to engage with this technology. So this talk is about Use.GPU, which is my attempt at doing something about this, which drives WebGPU. So WebGPU is the new web standard for GPU graphics. And it's also built on top of something called Live, which I wrote, and all of this runs in the browser. And what I'll be talking about is 5 things: incrementalism. I'll talk about the world of graphics versus web, what went wrong with GPUs. I'll talk about the live runtime and the Use.GPU components. And if there's one overarching theme here, is that live completely changed the way I think about code. It just did. So I'm going to start with explaining live briefly. And just to calibrate, maybe raise your hand if you've worked with React. Okay, of the people raising their hands, how many of you liked it? I like a challenge. So live is a React clone. It very much is a re-implementation of many of the same ideas, but slightly differently. That means it's incremental. It avoids redundant recomputation. It's reactive. The dispatch and the data flow is implicit and one way. And it's declarative. So side effects are auto-mounted and disposed, and this is generally a good thing. And I think React did something very, very interesting. And I teach developers React. And I genuinely believe until you build Excel or Figma in React, you don't understand React. And I wonder if this is true for the React team, if they've actually done that. And I don't mean a spreadsheet or a drawing app. I mean Excel or Figma, cloning it completely end-to-end so that somebody would barely notice the difference if they're an Excel power user, for example. Now, this app is actually one of mine. It is a React app on the outside that takes care of this UI. And this here is a live CPU canvas. And I'm going to use this as an example to show what live is all about without any of the GPU stuff getting in the way. So this is a reactive canvas. It's pretty interactive. It's got those nice little floating labels. It's got highlights. It's WYSIWYG. And generally, that means a lot of state is changing as you interact with it. And the challenge is how do you keep bugs from sneaking in as you're constantly changing things in response to what the user does. And just for completeness, I have this little pop-up. This is, again, React HTML. So just to be clear what you're looking at. And the gist is this generally just works. I can combine React and Live through a mechanism called portals. This is actually a React thing. And the idea is you make it as easy as possible to transition from one world to the other in such a way that it still works. Now, Live has an inspector. This is what it looks like. And it's all about showing you what code is doing. And you see it flashes green when I move the mouse. That means code is running. If you don't see any green, like now, that means no code is running. And this tree is a typical React component tree. I can shrink that a little bit so you can kind of see the overall structure of it. It's not that complicated. And then all the stuff that's hidden now is all the stuff that's in the canvas, which is polylines, polygons, some labels, just shapes, right? Now, this being an inspector, I can point at things and highlight them, because why wouldn't you? And when I interact with the canvas, this thing lights up like a Christmas tree as it selectively runs codes in response to things I'm doing, but never really the whole program once it's started. So this is how I like to demonstrate sort of the incremental reactive properties of the system. It selectively reruns pieces of code. Each of those lines in the tree is basically a function, and that's how it works. Now, there's this thing at the end, resume multi-gather yeet, resume selection UI, and yes, I'm being serious. That does something special. And you'll notice that when I highlight elements, it highlights other things. In this case, in purple, all the dependencies. And if you know React, you know that this shouldn't be possible, that a parent or ancestor element depends on elements deeper in the tree. And that's basically the thing I did. I built Live so that I could extend React to return data back to the parent. And that's the trick that makes this work. Because in every other way, this is pretty much a React thing. This polyline has props, as one would expect in a React-like, and it is rendered using a JSX-like syntax. The interesting part is this multi-gather. What does it do? As the name suggests, it gathers things. In this case, all the event handlers for driving the canvas, as well as all the draws. And each of those things is basically a Lambda, or a Lambda with some metadata, that can be called to drive the canvas. So it gathers this all up. Each of this is a Lambda, a list of Lambdas in flat tree order. So it respects the top to bottom order of the tree, but it just flattens the hierarchy of anything that it's gathered. And what's interesting about this mechanism is that it makes most canvas libs completely obsolete, web libs, because what all these web canvas libs do is they just drive the native canvas anyway. They're just wrappers. They don't really do that much. And all you need to drive a canvas is exactly what this is doing, gathering up event handlers and draws, and then executing them. And this is very interesting to me because it shows that just by adding essentially one operator to React, you can make it do some really interesting things that are eminently maintainable. This inspector also, because it's reactive, lets you just inspect all the state live, because why wouldn't you? Very convenient. And this app also, if you look at the top left, has local undo, redo, as well as multiplayer. And this is an important fact because it means any value in the app can change at any time, no matter what the current user is actually doing. It doesn't matter where the focus is. It doesn't matter what's open or what's closed. You can undo and redo any change in the app. And I would say that this is why you should know React, or at least the patterns of a React-like in your language of choice, so that you can understand how to pull something like this off. Because for a lot of web developers, this is broadly black magic. And they don't have a path from their current code base to a undo, redo, multiplayer capable version. And just to clarify, this inspector is React-driven. So I use React to drive HTML because it works, it exists. And it's an instance of React prepared by the live canvas, which is itself mounted inside React. And that composition just works. Now, if I look at the code, if you know React, it should look like React code. It really does. It's a carbon copy. In this screenshot, there's only one thing out of place, and that's that type. In React, that would be FC. Here, it's LC for live components. And it has JSX syntax to render things just like React. So essentially, we should just be able to do the same to drive WebGPU, right? And then we would have a declarative, simple, elegant thing that would make most WebGPU libraries obsolete, right? That's the dream. Unfortunately, it's not that simple. This is where things get complicated, unfortunately. So graphics versus web. The world of graphics and web are two different worlds. Why? Because graphics is mainly driven by video games and industrial CAD. And that means large teams, very large teams sometimes, 200, 300 people. Offline delivery, so they prepare the product ahead of time and then ship it in a big thing. And then there might be day one patches, but it's still generally offline delivery. And the main thing they care about is rendering performance. And that means the projects tend to be quite monolithic. On the web, it's very different. It's mainly driven by SaaS companies, browsers, open source, small teams, maybe just 3 to 4 people. Continuous delivery is generally preferred. And the main thing we care about is compatibility. So the focus is on composition and reuse. And these are two completely different worlds. It affects how you build technology, how you do things, and so on. And this leads to a story that I call, how do I draw a friendly line? Because on the web, it's very simple. Use canvas. Context.linewidth is 5, context move 2, context line 2, context.stroke. That's how you draw a line. In the world of GPU graphics, what graphics will tell you is make a render target. You say, well, what's a render target? Fill a vertex buffer with triangles. Triangles, but I want to draw lines. Yeah, I'll learn a shader language, dude. Which one? Compile a vertex and fragment shader, build a pipeline with descriptors, and make a render loop to dispatch it. Chop, chop. Get on that. Yeah, says web. But web goes away and comes back the next day. Yeah, I get a black screen. Where's the debugger? Yeah, there is no debugger. And no printf. I'm not joking. I'm not joking. It might seem like I'm trying to start some beef here, but I'm really not. Because in truth, I am a child of both worlds. And I think they actually have a lot more in common than either side wants to admit. I think the applications are both multiplayer 2D and 3D content editors, if we're honest. There's a 2 to 3 year project turnover, or at least a staffing turnover these days. There's continuous bug fixes, decades of legacy craft, and it's only bearable with extra tooling, right? Install node and npm, make a package JSON. What's a package JSON? And if we get graphics and web drunk, graphics might say, you know, WebGPU is kind of shit, right? And web might say, well, yeah, browsers are kind of shit. But if graphics is being honest, graphics would say, well, Vulkan is actually kind of worse. Yeah, so is our backend. Something went wrong here. What went wrong with GPUs, but maybe with code in general? It's about immediate mode. What web was doing was writing just all the code to produce one frame, to draw the friendly line. You write all the code top to bottom, and then if you want to render something new, if you want to animate it or move stuff around, you just call it again with new input. That's immediate mode. It's immediate because it immediately does the thing. And this is very simple, but it doesn't scale. Why not? Well, you can't beat big O(n) if every input must be used. You simply can't. So the question becomes, big O(n) is fast when n is what? It highly depends. On a GPU, and in most other situations, you would use what's called retained mode, which is the opposite of immediate. And I have a function here of 4 arguments, and I want to call it on a GPU. What would I need to do? Well, first I have to allocate some GPU memory and upload some data into it for my A, B, C, and D. And then I have to compile the shader, which is the actual function. I have to dispatch it, and then await. So it's async. And you might think that that's the problem. How do I call a friendly function? But it's not actually. This is not the problem at all. I can deal with async. The web knows how to deal with async. It's not a problem. It's very different. It's about the shader dispatch. Because what a GPU is basically a massively parallel pure function applicator. You have a function, and it's going to get run on many, many, many threads, easily over 1 million, sometimes even more. And in order to make this useful, every one of those invocations has to have unique inputs. Otherwise, why you're just running the same code twice, right? Or millions of times. That wouldn't be useful. And that means the main constraint or the main bottleneck is memory bandwidth. It's just getting all this data in and out. So this is why we use something called spread policies to compress the data. Some of your data, like in this case A, is always going to be one-to-one. That's unavoidable. That's kind of what you want. But other things, like these colors, they might repeat, modulo 5. So you only need 5 colors, and all the other millions of threads just repeat. For these images, I might have a lookup, and I just put a small int in every thread, and then it can go fetch the right image from some kind of list. And D in this case is just constant, so I only need to pass it in once, and it just gets spread over all the threads, right? And in your first week of learning GPU programming, this is what you'll learn, that every one of these access patterns has a funny, unique, jargony name, but other than that, it's pretty much just, indexing an array using the thread index I in various ways. Simple, right? Yeah, no, here's where it gets weird, because there's also something called storage, which is a big array that you have random access to. So how does that relate to the bottom stuff? The bottom stuff is legacy craft. And it's not just any legacy craft. Trigger warning for functional programmers. There's completely different types and APIs for each of these things on both CPU and GPU. And if you want to change from any one of these index access patterns to others, you have to rewrite all the glue on both sides. It's kind of crazy. And so this is legacy craft that they still expect you to use. Also, there's restrictions on control flow and grouping, because, yeah, why not? And I call this problem number 1. And we're getting deep into the weeds here, so I apologize, but I can summarize it very simply. The GPU vendors tell us, batch everything. Do it. Just do it. So I say, okay. Yeah, no, not like that. There's a second problem called pipeline dispatch, where I have a very simple function of one input and one output, and I'm just going to map every pixel in that input image one-to-one. There's no spread, nothing at all, no spread policy. This should be the simplest possible thing that a GPU can do. How hard can it be? Well, this part is so damn complicated, I'm not even going to say the words, I'm just going to talk about colors, because the words don't matter. For the input, which is blue, I need 3 blue boxes, obviously. And for the output, which is also blue, it needs to be purple, and I need 2 purple boxes. For the parentheses, I need 2 orange boxes. And for the function itself, I need 2 green boxes. So yeah, 1 input, 1 output, right? No, sorry, I lied. There's something called the vertex buffer that you need in this situation also. And I know I said I needed 3 blue boxes for that 1 input, but no, actually, usually you need 5. That's all the stuff you need to call this simplest possible function. You wire it up like this, and you feed it into a GPU command encoder. If you order it by construction, it kind of looks like this, except there's all these type constraints that bind this thing together in very weird ways. So it's not even a very clean construction, because the very start depends on the later parts. And that's how you call a friendly function. The calling convention is a big nested data structure, roughly this type. And this is, again, a simplification because reality is worse, but I don't want to get into the weeds. And so this thing is problem number 2. Why is it like this? Well, I'm going to do something crazy. I'm going to teach you how video game renderers work in 30 seconds or less. Get ready. For purple of things, set purple. For orange of purple, set orange. For blue of orange, set blue. For red of blue, set red. And then we draw. What this means is these 4 nested for loops require that everything is set up and grouped ahead of time. And the inner loops change state more granularly than the outer loops. And that means this whole API is over-optimized for one way of doing retained mode 3D graphics. I'm not exaggerating. There's literally only 4 bind groups that you can use for the 4 for loops. And to this day, that is what we're stuck with. But I want to compose functions. Not going to happen. Sorry. There's a big issue with the setup as well, which is if the size of the data changes, you need new storage and upload. And if the type of the data changes, you need new everything. And this is a problem for me in particular because in data visualization, types are actually data. You don't know the types at compile time because you're building data visualization software whose purpose is to ingest any type of data. Literally, the types are data. And this has an effect on what you're doing, because what graphics is telling us is track all the resources and cache them, deal with async, pack all your data in binary arrays. Chop, chop, get on it. Yeah, I want to draw lines. But in the longer term, it really affects your entire development process, because they're basically saying you have to pre-process and bake all the data. You have to hand-tune the performance, which means forking your tech stack and fixing all the new bugs. Yeah, I don't have time. So these are the 2 major problems that I think we currently have in GPU land, at least when it comes to rendering. And there are things happening in the scene. There's Uber shaders, there's meshlets, there's nanite. But I say, how do I please draw a line? If you can't do that, what is all this other stuff good for, right? And there's a point I'd like to make that's maybe a little bit philosophical, but also quite literal, which is an atlas, which is this thing, is just a spicy memory allocator. So when you pack things inside a larger image like this, it's a memory allocator. We call it an atlas. And here, a retained mode is really the solution that causes the problem. Now this atlas is generated using Use.GPU's algorithm. It doesn't do any backtracking, and I'm pretty happy with this, all things considered. However, there's actually a trivial solution to this problem, which is order all the blocks from large to small ahead of time. And this exact same algorithm will produce this instead, which is almost the naive solution of just going in rows, right? It's a little bit more packed, but it's barely improving upon that naive solution. And I think this is important to realize that a lot of the things that we encounter in traditional mutable states and object-oriented programming is we're creating solutions for problems that we created using our solutions, unfortunately. So the live runtime, what is it? Well, I mentioned immediate mode. Write all the code to produce one frame. Call it again with new input. Very simple, doesn't scale. How can we improve upon this? Well, incremental mode. We're going to write all the code to produce one frame, but we're going to memoize the slow parts, save the last input and output, for example, these 3 blocks. And then when I call it again with new input, I can check, has the input changed? If not, I can reuse it. So for example, this first block we can skip, the second and the third block we can't, because the input has changed. So it's still pretty simple, and it's retained, right? But it's retained in a way that doesn't inherit a lot of the issues with classic retained mode, like the fragmentation and the allocation and so on, because you're still kind of running stuff top to bottom. It feels like immediate mode. And this leads to the next step, which is reactive mode. So you're going to write all the code to produce one frame, and you're going to memoize the slow parts recursively. So that, and then you rerun subtrees selectively. So in this situation, compared to the previous situation, you might only rerun those blocks, and everything else is memoized. That would be nice. This is very complex, but it's super retained, right? Well, it's so retained that it's basically Turing complete. And in practice, this only works when you use immutable data. We don't really know how to do this mutably. And so this is basically what React did. React lets you build reactive mode trees. So I'm just quickly going to go through that. And the way this works is you have an app that is going to render subcomponents at runtime, in this case 4, and it passes data along. So data always flows from a source into components, always one way. And these components are just functions that return child components at runtime. So app, in this case, returned 4 children, and each of these blocks is another function that can return other things, like so. And by returning child components, they're really declaring it because they do so using JSX syntax, like so. And this tree knits itself together at runtime by recursively evaluating until it stops. And if you're not familiar with JSX, it's a recursive data structure that you could kind of read like this. So every one of those tags is just a deferred call to a function with some arguments that you're passing to that function. And deferred calls are themselves used recursively as arguments. So in this case, I pass 2 greens to the orange, and orange can decide what it wants to do with that. It could render them directly as its children, or it could do other things, decorate them, ignore them, anything. It's all about giving control to every component to do what it needs to do at its point in the tree. Components whose state are stateful, and when their state is changed, they are rerun, and they can return new children, and the tree will re-knit itself together at runtime. And the deeper in the tree, generally, the more frequently it changes. So what you can do is you memoize components to avoid updating slow subtrees as a remedy if it's too slow. Now, React is used to drive HTML, and how it does this is it kind of proxies. So you have these HTML elements that are really special components or placeholders. And what React will do is it will use the tree structure as the page structure and create a new tree that's basically just a subset of the nodes of the original tree to render the HTML on the page. And in the process, as the top tree changes, the bottom tree updates in sync, and this is called reconciling. That's the main mechanism. And reconciling is important because it makes what React does feel like immediate mode. You don't think about the changes, you just declare what you want to happen. One more thing to mention about React is that while it is a tree, you do have contexts that allow you to make skip links. So this is a link between a distant ancestor and a particular child. There still has to be a tree relationship indirectly, but you can skip. So that means it's a directed graph with a tree for a spine, essentially. So that's React. What about Live? Well, like I said, Live inherits a lot from React, but there's one big difference. There is no HTML. There are only hooks, essentially. That's what Live has. It has functions that have hooks that return other functions that have hooks. And this, there's a similar thing happening where there's a first tree and Live can drive another tree with that, but they don't have to match. And then the question becomes, how do you extend the React model so you can return data without breaking one-way data flow? And how I did this is quite simple. I just glue a mirror image of the original graph onto it, like so, a reverse shadow tree, you could call that, which are just, buckets that you can throw data into. This is the yeet operation, which is, etymologically sound because it's a throw for values instead of exceptions. And that's why it's called that. Also, yield is a reserved keyword. I can use yield. So this is the closest thing. And then you do an incremental map reduce on that second tree to gather it all back up into one value. And that one value you can pass to a continuation to do stuff with and spawn new components, right? And so this functions basically like an incremental version of await. The way you use this in code is you return, in this case, you can express this in JSX syntax, but it's even uglier. You return essentially a function with the children, a mapper, a reducer, and then a continuation. And for the specific case of just gathering up a list of values, there's an operation called gather, and there's also the multi-gather that I showed you earlier, which is collecting a struct of arrays. And this ugly continuation passing style is unfortunately needed because JavaScript and Typescript do not have rewindable generators, and I'm not sure anybody else does in a way that would be useful for me. But this is basically what you could call the live effect system, where you can keep doing this. You can do additional reductions on the second tree. So you can recurse and make lots of trees in sequence. You can also nest those reductions at any point. And basically, anytime you see something like this, it's basically just a spicy function call. It could hide a whole new subtree, as one would expect. There is, however, a problem here, which is that there's obviously only one return value to this continuation, which means in terms of data flow, it's a bottleneck. And sometimes bottlenecks are exactly what the problem demands. Like in layout, for example, if you're doing 2D layout, you need to know everything that's on the page in order to lay it all out. So there is inevitably a bottleneck. But often there isn't. What can we do then? Well, Live has something similar to reconciling using a concept called quoting, which you may be familiar with from parentheses-based languages, where I can again make a second graph or tree that is just a subtree of the first one. And through reconciling, these two are kept in sync. So what does that mean? It means that, for example, this yellow component at the top is quoted. The top version isn't real. It's really just a placeholder. The actual instance lives down below, and that's where the state is and everything. And so the data flow here, and you do this using this quote operator, and you can unquote to basically do the Lispy thing. So the data flow starts from the root of the app, would reach this first quoted node. That would mean it would go down, render that there, then go back up in an unquote, hit the red component, go to the yellow one, render the yellow one, and now we're done. So it's still a one-way data flow that is well-defined, and there are no cycles here. And you can add reductions on either side independently and there's still no cycles. And now because of the recursive property of effect systems in general, that means this tree could itself be reconciled from something else up top. And so it's such that the data flow would actually be, it started there, it went down, it double quoted down, and then eventually after going through that zigzag, it went back up. And what you have here are essentially incremental Lisp macros, where you use effects to reconcile other effects, which is very interesting to me. And this is sort of what your program structure starts to look like when you program this way. And it might seem like this is super abstract. It's just boxes and arrows. Does it even mean anything? But what if we were to graph a certain data structure onto this? Would it even fit into that world? What would the impedance match or mismatch be? Well, these dotted lines are constraints. And those are actually not really a problem because in a data-oriented architecture, they are going to come from a single source of truth. It is going to be correct by construction. So for the most part, we can ignore those. However, this data structure, and this is correct, this isn't just abstract, it's all correct. It's like Portal, the signs are right. These lines do not make it a reverse tree. It's actually just a DAG. However, there's a distinction here, which is that the top one is a value dependency and the bottom one is a type dependency. And I said if the type of the data changes, you need new everything. Well, everything is rewindable, so that's actually not a problem. Not at all. We can just ignore those for the purposes of fitting this thing in here. So you actually do have a well-formed data flow graph that you could throw values into. And if you were to connect each of those boxes with its source by hand, it would be quite unwieldy. And I think this slide shows that there's a flaw in graph-based programming. Where it doesn't really allow structural reuse. And I think this is why graph-based programming tools are kind of doomed, inevitably, because you end up always with a tangle of spaghetti. However, if you align the left and the right side like so, what a coincidence, then you can basically, implicitly connect things. And to functional programmers, this should probably not be news. However, I still think it's important to point out that this is so. So the big question is, how much of this is metaphor versus literal? Well, here's the deal. In Use.GPU, there is a big, giant reactive mode tree that sits above, exactly as implied here. I track all the dependencies. I do all the heavy lifting with reductions and reconciliations. And at the end, there's a GPU dispatch over a pretty hard boundary with something completely different on the other side, different hardware. So that's all true. The only part that isn't true is this. The WebGPU glue is not actually effect-based because that would be too inefficient. So instead I use React hooks, which you can think of as inlined reactivity. It still obeys all the rules of React. I can still rely on certain invariants being true, but I don't actually, do this in the component style that React uses because that would be too heavy and there wouldn't really be any reason to do so. But in every other way, we can kind of pretend that this diagram is true and we can reason about it. That's the important part. And I think this, I said this working with live changed the way I think about code, and I think data shapes the code that generates it. I really do. However, data also shapes the code that consumes it. And this leads to a big question, which is whose job it is to align or convert the structure of data, especially when you work in an effect-based system where the structure of data is also the structure of the code, and effects are values that you produce at runtime, essentially. And this is how I think about Conway's law now. People have a different structure of their data on both sides, which they chose because they have certain ideas about what code they want to process it with. They're different across the boundaries, and they never quite align it. They just, put converters in both directions in the middle. What's the catch here? There has to be a catch, right? There's no way that this could possibly work. Well, there is one, and it's a pretty big one. Like I said already, this only works with immutable data, which in the world of graphics is kind of, it's an issue. We have, many hundreds of megabytes or gigabytes of data. You cannot do that immutably. It's not going to happen. So everything is passed by value in the system, which has implications. If there is a lot happening up there above, our current flow, then this thing is changing very often, which means you can't memoize it. It would be pointless. It would be constantly, it'd be a cache that'd be busted constantly. But if you pass by mutable reference and you use mutable data, then from the point of view of value, of by value changes, this would never get called again because the mutable reference hasn't changed. So from the point of view of reactivity, there was no change. It only ever does shallow comparisons. So that wouldn't work, and you wouldn't be able to continue because the code literally wouldn't run. Now, there is a way to fix this using something called declarative signals. And unfortunately, this has nothing to do with what most people in the front-end world currently are calling signals, just to be clear. But you can fix this. It just means that you're kind of, you stop relying on the data flow properties of React or the React-like, and it seems like, you're putting on your cowboy hat and you're going cowboy coding, which is generally true. However, I think I staged that wrong. However, in a CPU-GPU scenario, there is actually a very good reason to do this, which is, as I said, you've already uploaded the data to the GPU earlier, and it happens out of band, like so. And that means you can pass handles by value. You don't need to pass the data that's changing. And these handles never change, even if the data underneath changes, because it is also a mutable reference. But you formalize the point at which you mutate as the upload across the device boundary. And that's when you put the declarative signal in, which is, that's a system and rules that you can follow. And there is still one problem, namely if the size of the data changes, you need new storage and upload because it's a memory allocation problem. You need to move data. You cannot pin it if it needs to change size, which means wherever the upload is happening, that needs to move the data to a new buffer, either by just re-uploading it or by doing a copy, by dispatching a copy on the GPU. But still, that means only one handle is probably going to change, and that means you can still usually memoize. So this isn't too bad. Now, this declarative signal thing, I do want to explain this because it's a subtle point, and it took me completely by surprise when I ran into it, which is basically incrementalism breaks functional programming. Yeah, I'm sorry. Suppose you have a couple of lists just with numbers in them, and you concatenate them. Very simple. In pure FP, concatenating with an empty list would obviously be a no-op. It has no effect on the output, and you cannot tell that it was there. It's completely unremarkable. However, in incremental functional programming, this is not a no-op. Why? Well, it depends on whether you pass in the same empty list every time or a different instance of an empty list every time, because that determines whether you're going to recompute the output. That determines whether the output is going to be the same instance as before. So even if all you have is pure functions and immutable data, nevertheless, as soon as you remember previous values, you can always tell that something changed in the input, even if by a deep comparison, the output is unchanged. And you can kind of make use of this. Why? Because in practice, I don't emit an empty list and then run the code again just to compute the same result anyway. A declarative signal is recognizing that there is a no-op here that we can optimize away without invalidating caches. We just have to let the code run again, even though by the normal rules, the value would be the same and it wouldn't need to rerun. But we've remembered that there was actually a declarative signal involved that basically busted the cache without throwing away the contents because the contents are actually still valid. So that's declarative signals. This was surprising to me, but I ended up making good use of it. So that's it. You can kind of also think of the empty list as, for example, a no-op draw call, a no-op dispatch to a GPU, which again, there's no reason why you can't just optimize that away and deal with it out of band. The other thing I'd like to point out is this general sort of pattern, because it's effect-based programming, you can think of the boundary between a server and a browser also in a similar way. And maybe some of these patterns could also be applied there, with the question being, what does push versus pull mean? What does quoting mean here, and so on? And that's unfortunately a topic for another time. But I think it's very interesting. When you think about, like I said, web backends tend to be nightmares too, and the way the code is split over backend and frontend tends to suffer from the same problems. Maybe similar patterning could help there. If there's a conclusion to this part, I would say this is just normal code memoized. It might seem like I'm throwing a lot of jargon and new patterns at you, but it's not. This is what happens when you memoize normal code and you actually deal with all the fallout of that choice. That's what I think is interesting about React, is that they figured all this stuff out and came up with patterns that you can teach to juniors and that they can reasonably follow to pull this kind of stuff off. There's another thing here, which is that I think incremental effect systems kind of act like virtual reified silicon. You spawn all the components that you need to execute your current code path, but in such a way that it's really easy to calculate a whole host of adjacent values. If only a few of the inputs change, you can still reuse the bulk of the data flow, and you don't need to rerun everything end to end to handle a very wide set of potential changes. Should this be a language? Because I just wrote it in Typescript. And the reason I wrote it in Typescript is because I didn't want to spend all this time designing a language only to discover that it couldn't work. I would much rather make it work first and then ask the question, should this be a language? So that's what happened. And that led to Use.GPU. So what is Use.GPU? Well, it's very simple. You take the typical code that you would write to render one frame in WebGPU, and then you memoize it using the patterns of live. You can make it an interactive app using live hooks, and then you just kind of go all the way, see what happens. Do you hit a wall? Can you actually just do this? It leads to some interesting results. How do I draw a line? Use GPU plot, line, done. And you see those little spinning squares. It has animated CSS transform-like things in there that allow you to do that relatively efficiently. So it does 2D, 3D, and 4D if you really want to, because that's how I roll. How do I draw many lines? Well, interestingly, you still just only use one line. And this goes back to the advice, batch all the things, batch everything. It's much more efficient if you know that any command you do can automatically be scaled up to n copies to bake that into your APIs. And what's interesting here at the bottom is I have, this is drawing 2 lines, each of 4 vertices. But I only pass in 2 colors, and it's automatically going to spread. This is the color of the first 4 values, and this is the color of those values. It has a sensible way of notating spreads. And if I passed in colors instead of color, then it would just be one-to-one color here. So it has a pretty elegant notion of spread that just handles a lot of common cases, so that all these different things here were actually, they just all look kind of like this with variations on that pattern. There's line, there's point, there's polygon, and so on, all the usual shapes that you expect, and they kind of just work, and they look pretty decent. So I designed sane APIs for the common use cases, and I try to provide zero-cost escape hatches for the rest, although zero cost is, I fully admit, this is an underspecified term, because what your notion of zero cost is depends completely on all your assumptions. Earlier today, Jonathan Blows said, everything he did with Jai is compile time. That doesn't work for me because my types are data. I literally cannot do it at compile time. So my notion of zero cost is quite different. Sorry. So this thing here, this is another example. And I'm not going to focus on too much of the glue around it because a lot of this is boring computer graphics stuff. I'll just look at the core stuff here, which is I have an environment with a cube map, which is the thing that's reflected in these balls. There's an environment preset, which is basically what it looks like when the cube map hasn't loaded yet. And then I create 8x8 spheres, copies of a mesh, with a PBR material. This is physically based rendering with some parameters, right? And that's what this looks like here. I have 64 shiny balls. And on the left is a gigantic tree. It's quite a lot bigger than the CPU-only version, right? And that's the curse of GPU, basically. Now, this is a demo app that has like lots of different demos in it, so that's what the outside is kind of about. I have a WebGPU canvas here, and an event handler there that lights up when I move the mouse, right? And right now it's freeze framing, so that's why it's lit up. Oh, I have a video not playing for some reason. Go down, okay. So what else is in here? This is the cube map loader. So it loads 6 images for 6 faces of a cube, and then it's going to run a bunch of compute shaders on that. That's there. Quite a lot of dispatches. Down here, we have some more stuff. I have some camera controls that light up when I move the mouse. There's a render target there. What's a render target? Well, it's one of those things. And there's a forward renderer here. That's, again, a term of art. The point is I could swap this with a different kind of renderer just by swapping one component, and everything else should still kind of work. And then down here, I have this PBR spheres. That's quite a lot of them. There's 64. And this is enough overhead to make Casey Muratori upset. I have no illusions about that, so I'll just keep going to the bottom. Where I have a tone map, this is the thing that makes the colors pop. It deals with HDR, dynamic range, and so on. I have some render passes there that are accumulated. And then at the very bottom sits a GPU dispatch from a reconciled dispatch queue. And also there's the HTML UI, which is just React. And so React is just an effect inside Live, and Live can just be an effect inside React to nest the two. And that kind of just works. So that's one example. Here's another one, which is a little bit more advanced. And I'm just going to focus on this part, because this is a voxel model. And that's a self-contained module to deal with voxel models. The only thing I'm injecting is 2 components. One is a loader that takes a URL. The other is the actual thing that renders the vox model. And that's literally the only new thing I add to be able to do this, right? And I'm not going to go through the full tree because it's too much detail. This is what it looks like. So you have this propane tank model from a game called Teardown that I'm rendering here with some moving lights around it. Now, you might think it's made out of a bunch of individual cubes, but not really. If I turn on a debug shader, you can see what I'm actually telling the GPU to do is just draw a bounding box. And then on the surface of that bounding box, I run a ray tracing shader that is going to traverse the volume of the voxel file, where every voxel is just a byte inside a 3D array. And the coloring that you see is how many steps it needed to find the right intersection. And the bulk of the voxels is blue, which is like 2 or 3 steps at most. And there's around edges, it's going to need a couple more steps. But overall, this is very efficient. Now, this checkbox, when I clicked it, it required an entirely new rendering pipeline to be set up. And so I'm going to uncheck it and immediately freeze, just to show you. This is all the stuff that lights up green when it goes back to the old rendering technique. And that, it's again sparse. There are large parts of the tree that aren't running. And if I press play now, it immediately stabilizes, where again, almost all the code is not running. The only thing that's running that's green is the moving light. This is the shadow rendering mechanism. And you see down below that yeet lights up. Why? Because the shadow pass reconciled a dispatch there. So this is a concrete example of how reconciliation is used to assemble new trees out of much more complicated things. This shadow renderer thing with this TIE fighter cockpit looking thing is a cube map renderer. It's rendering the scene from the point of view of the light with the kind of a psychedelic debug shader. This is the view down onto the tank you can see here. And so using these 6 cube faces, it can determine shadowing on the actual scene here, where you see that moving shadow from that light. And that's how it does that. Now there's a couple of interesting things to note here. One is that these components aren't actually green. They're black. There's no CPU code running in that component itself, yet it's moving. Why? Well, because this is running on the GPU. So that component reconciled the dispatch, and that dispatch is, at the bottom of the tree, there's a little bit of green that is continuously running, but it's just dispatching the same command over and over again to make this happen. The other thing is, because this is happening purely on the GPU, this data also only lives on the GPU. So how am I displaying that inside a React-based inspector? Well, it's a canvas. And how do I drive a canvas? Well, with live. So there's a whole other instance of live in here that has some fun stuff in there to drive the view that I just scrolled through. So this is live in React and Live. And on the left here, I have effect-based layout components, so that ultimately, to render these things on the right, you can see it's actually 2 triangles for that thing. When I highlight it, it shows the raw geometry underneath. But it's actually assembled from, an HTML-like system where block and element and inline and text are effects that have a head and a tail, like here so, that is using all the live data flow stuff to work. So this has a block layout, flexbox layouts, the text at the bottom there, depth 32 float, that's also GPU rendered. The scrolling is driven by the GPU, and it has a pretty good facsimile of macOS font rendering, because that's how I roll. And also, this inspector, just to be clear, is React and Live in React and Live. Why? Composition and reuse, right? React is in effect inside Live, Live is in effect inside React, and they kind of just work together, and everything is synchronized on both sides without me having to worry about it, without going crazy, and without violating the invariance of the system. And again, to some people, this might just be unremarkable, but I can tell you, in the world of graphics and GPU rendering, this might as well be black magic. Their architectures don't do this. They don't think this way. They fuse everything into big, giant machines. And this composition thing is also an essential part of the shader mechanism. So how did this voxel thing inject itself into the rest of the system? Well, using shader composition, which is done by Use.GPU shader. And this is a shader linker with a module system in WGSL, because that's what grown-ups use. Most shader languages do not have module systems, FYI. Again, what might be super obvious to person A is not super obvious to person B. And the other thing I do is I turn inputs into getters to basically get rid of all the legacy cruft. So instead of accessing an array directly, which you wouldn't actually write in this simple, obvious way, I make a linkable function, getValue, that's a getter with an index, right? And by default, I might put in just a stub that says it's just going to return a constant. But I could link it with another function that returns a different constant. I could link it with a function that accesses an array. I could put a piece of shader code here to compute the width dynamically. This solves spread, basically. And it solves it pretty well. And I do it by ignoring all the legacy cruft, basically. That's the solution. Throw it away. You can then import these shaders into Typescript. And what you're importing is essentially a pre-parsed version of the shader, which you can then bind arguments to by handle, by reference, or by Lambda. So you've uploaded your data to the GPU ahead of time using another hook, and then you bind it as you would just pass a list of arguments to a function in the order that they were defined in the shader, because that's how programming languages generally work. And this function's essentially like shader closures, where the data travels along with this shader function. And I could use, like this is another function, getVertex, right? And this gets linked into a stub that has the right signature. And that's kind of how the material system is extensible. It's just all linking functions together with, as closures with the data traveling along. So this is kind of what the output looks like. This is what linked modules look like. It's mostly just concatenating and prefixing stuff, and then generating this ugly binding nonsense. It can also aggregate structs, like here, in a few different ways, and it generates boilerplate and bindings. So you never have to write this stuff yourself. You just purely deal with the functions, and you define links that end up getting replaced with other things. So much boilerplate, you really have no idea. This is just all bullshit. And I do it all at runtime, because like I said, my types are data. I cannot do it at compile time. I do not have that luxury. If I change one detail about how I render a friendly line, I need a completely new shader, potentially. You can inspect these generated shaders and their bindings using the same inspector. And what do I do with this? Well, this is the layout system given its own little demo. So you can see it kind of just does HTML-like layouts. It's fully scalable because this renders using distance fields, signed distance fields. And what that means is everything's basically mathematically defined, like so. And I can visualize this is a contour diagram, essentially, of all the distance fields. And so the text is distance fields, the boxes are distance fields, the emoji are distance fields. It all kind of works. And it's a good approximation of a minimum viable box model for HTML. I do, however, want to emphasize this is rendering only. You can't really build UIs with this yet, and I don't have that ambition right now because browsers exist, HTML exists, React exists. Everybody knows how to use that. This is bizarro land. It's mostly used for debug UI. But I wanted to do it properly because if I'm doing debug UI, I want all the same luxuries that I do have in HTML. I want to be able to do flex layouts and so on. So this is rendering with distance fields. This is a prototype that's not public. It's a prototype of a lighting engine with ray tracing. And the thing is, this isn't state of the art by any means. It's a little bit grotty. You know, computer graphics experts will probably scoff at this as being so 17, something like that. So passé. However, this demo does something neat, which is I have a ton of debug visualization. Like here, I am visualizing a bunch of rays. And how do I do that? Well, I printf rays in a shader. Why wouldn't you? And this uses all the standard, the same line and point rendering that all the other stuff uses. So line layer and point layer is what those plot primitives that I showed earlier end up as when they're aggregated. And I just link a function, emit line, emit point, which is basically, you know, print line, print point. And I can give the coordinates, I can give it a color, I can give it a size. And that's what I link with my shader. I don't have to reinvent the wheel just to do this, which is very nice. And this is another fun thing that I worked on. It's the opposite of state of the art. This is graphics rendering circa 1999. It's a level viewer for dark engine games. So System Shock 2, the Thief series. People are still making levels for this, and I enjoy those games. Point is, this is the most fun I've had with GPU development in ages, making this. It was a very fun exercise. I can kind of just do what I want. And grafting a 1999 rendering pipeline onto Use.GPU is very simple because I could do it all through shader composition, essentially. So let me wrap this up. Use.GPU works today. If by working, you mean you have WebGPU support in the browser. But Use.GPU is a what if. Why? It's really only a vertical slice, as they call in the gaming industry, of all possible components you could have, because the GPU API is in the way. I can try and solve problem number 1, but I can't do anything about problem number 2 because that's silicon. And general purpose GPU programming is basically Dark Souls. You have only 4 equipment slots. Good luck. And oh, you have to craft all your own equipment. I think the industry is kind of in denial To be fair, on the web side, multi-threading in browsers also sucks. So incremental effects. What have I learned? These trees are basically a finite and semi-static stack trace of everything that happened, where continuations are fences to prevent out-of-order evaluation, and the app structure is also a data dependency graph. And this alignment has some really interesting properties, where your entire app acts like one big main function. This is something Carmack used to talk about, and that was actually cited today earlier by Adam, the QuakeCon keynote. And it's basically a DSL for the target data structure with a hierarchy of change ordered by granularity. The CPU code acts like a JITted GPU, right? Like sort of reified silicon. And your CPU code acts like immediate mode. I think this is very valuable. I think incremental effects are a very interesting programming pattern, basically. You can also apply this scheme to some other things, like words. Words are a finite and semi-static log of everything that happened. Your entire story acts like one big main function, basically. This is Chomsky. I think maybe sentences and clauses are fences to prevent out-of-order evaluation, which means it's a DSL for the target world. I think the story structure is also a data dependency graph with a hierarchy of change ordered by granularity. And an LLM, as we kind of discovered, acts like a JITted world. And I think that's because a language is an effect system that orders information by how often context changes. You might call that Zipf's law 2.0. That's my conclusion. Personally, I prefer shapes. This talk, I have mounted components, I have reconciled trees, I have reduced information, and I have quoted, and I have quoted. But maybe mounting components is just calling functions. Maybe reconciling trees is just diffing maps. Maybe I'm just returning values and sandboxing things. Maybe that's all you need to make Use.GPU. I went massively over, I apologize. You can find out more at usegpu.live. Thank you.